So the next we'll solve one problem using Galerkin method. Find the expression for displacement u of a bar that is subjected to distributed axial load q naught per unit length. Now this is the bar which is subjected to distributed load, that is q naught per unit length, having area A, Young's modulus E, and length L. Now first step is we have to define the boundary conditions for this problem. Essential boundary conditions, that is at x is equal to 0, u is equal to 0, at x is equal to L, AE into dou u by dou x is equal to 0 because there is no load here. Or we can write it is nothing but dou u by dou x is equal to 0. Now, so first step, that is formulate differential equation of equilibrium. Formulate differential equation of equilibrium for the given problem. So that is, this is a bar problem. So for a bar, it is governing differential equation is AE into dou square u by dou x square plus q naught is equal to 0. Now second step, assume a displacement function. So displacement functions, let us assume u is equal to a naught plus a1x plus a2 x square. So the degree of the polynomial, so the minimum degree, that is depending upon the boundary conditions. Okay, essential boundary condition. Here the boundary conditions are 2. So the minimum degree should be 2. Okay. And also in governing differential equation you have dou square here. So degree is 2. So minimum is the degree of the polynomial assumed. Suppose you are assuming a polynomial, it should be 2. If you assume minimum, so less than 2, then there will not be any residue, so it's not possible to solve the problem. Now the boundary conditions are at x is equal to 0, u is equal to 0, at x is equal to L, we have dou u by dou x is equal to 0. Now if you apply the boundary condition, we can write, if you substitute at x is equal to 0, u is equal to 0, we can write a naught is equal to 0. Now therefore we can write u is equal to a1x plus a2 x into x square, or we can also, if you differentiate with respect to x, the above expression can be written as a1 plus 2a2 x. Now if we apply, so the second boundary condition, we can write, that is dou u by dou x is equal to 0. Suppose if I substitute dou u by dou x is equal to 0, we can write 0 is equal to a1 plus 2a2, that is x is L. L X is L. So that is nothing but we can write this as A1 is equal to minus 2A2 into L. Now we got A0 and A1. So substituting this A1 and A0 here, we can write therefore U is equal to, so substituting values of A0 and A1 in displacement polynomial U, we can write U is equal to minus 2L A2x plus A2x square. That is nothing but U is equal to, if you take A2 outside, you can write x square minus 2Lx into A2. Right. So the next step is, that is, we have applied boundary conditions, we got the modified expression for displacement, but as we have assumed the polynomial or displacement function, so if we substitute this back in our governing differential equation, we get some error or residue. So that is nothing but, so third step, substitute displacement function into differential equation. So that is nothing but governing differential equation will be R is equal to E into E into dou square U by dou x square plus U naught. Okay, so initially it was 0, but now if you substitute U here, you will get some residue. So we need double the differentiation of this expression. So suppose if I differentiate once dou U by dou x, we can write this expression as 2x minus 2L into A2. Now once again, if I differentiate dou square U by dou x square, I can write this as 2 into A2. Now if I substitute back here, therefore I can write R is equal to dou square U by dou x square is nothing but 2A2. So that is A into 2A2 plus Q naught. So next we have to minimize the error. So we have to use the Galerkin formula. So use the Galerkin formula. So that is integration 0 to L Wi of x into R of x into dx, that is equal to 0. So the value of I here, it is 2. Okay, so there is only one unknown here, that is A2. So this will become 2. Suppose if here it is A1, then the value of I is 1. Okay, so therefore I is equal to 2. So substitute I is equal to 2 here. W2 of x into R of x is R into dx is equal to 0. So substitute for W2 of x is nothing but the variable along with A2. So that is 0 to L. W2 is x square minus 2Lx, x square minus 2 into Lx into R is nothing but AE 2A2 plus Q naught, that is 2A EA2 plus Q naught into dx, that is equal to 0. Next we have to integrate. So if you integrate, you will get x cube by 3 minus 2L into x square by 2 limits 0 to L into 2A E A2 plus Q naught, that is equal to 0. Now from this we can write what is A2. So therefore A2 is equal to minus Q naught divided by 2 into A into E. So now we got A1, A0, A1 and A2. So once again, if you substitute these values, so suppose I have already substituted A0 and A1 here and I got this expression. Now if I substitute A2 here, I can find the displacement at any point. So therefore, fifth step, find the unknown displacement. So substituting the value of A2 in this expression, we get the displacement at any point x, that is u is equal to A0 is nothing but q naught by 2AE into 2Lx minus x square, right? So this is the final expression.